Yeah, Robert, have you been able to watch Wall or Silo?
I don't know if I want to start watching it. Do you think I should?
Oh, because you're gonna. I would read it first.
I want to read the
Yeah, I would
first.
read it first. Yeah,
Okay.
yeah, definitely read it first. It seems like, I mean, they're only up to episode 3 in their release schedule, but it seems like the story has been reorganized a little bit for screen. So with Hugh Howey, apparently he's heavily involved in it, so it wasn't just some other people coming in and cutting stuff out or changing things. It's almost like some parts of it are like a different view of the same event.
Just joining.
So I think reading it first, and then at least the first book. I don't think this first series will go past the first book. So
okay, so the first season is well, the first season or whatever it is. It's going to be the first book, Silo, right?
Yeah.
Then it was it Wool and?
No, it's Silo, Shift, and then Dust. Yeah, and Wool was like the name of the first. Like it was like he started with a short book, which was called Wool. And it was popular, so he built sort of the rest of the story out from that short book, and that became Silo, which was the first. Oh, sorry, yeah, the first book, essentially. Oh, that's tricky. So I haven't looked. I think when were you wanting to schedule that meeting?
Was 11:30, but Melodies just send an email saying 1:30.
So 1:30 should be okay for me. I do have a meeting at 1.
Yeah.
But that doesn't usually go longer than half an hour.
Well.
And it's probably important to have Melody there.
Yeah. I thought that might be good. A lot of technical knowledge.
Yeah, especially with the conversion of trees and strategy.
Strategies. Wallpapers. Not the goal. Strategy. You know, like, sorry. How do you do that? Oh, that's TPD.
Have you managed to work with any parallels?
This is the strategy.
Things of innovation.
Oh, yeah, strategy.
The bathroom is.
You can stuff there or something. You can reuse the same variable. Save memory. So you have a big array. And you modify that array. Variable name. Copy the memory twice to do memory something. What you do is I have a really big array, an array of 8. Instead of having an array for a variable, have an array when you modify it. Yeah. Because there are certain functions in Python that secretly copy your array. So when you input your really big array, even though it returns one array, the process makes like 4 of them. And so it can just flow. Like you might think that you only need 5 gigabytes to run this whole wide, but actually that hidden backside actually makes 20 gigabytes. And that's like much of something. Doesn't matter. I ran into a bunch of these things. I was really annoyed. So I was like, I sold them. I just everything's called the same variable. Yeah.
Do you have any reasons for lunch? Yes, no requirement.
But I'm not saying it's a 10-year. It's 10 years.
I mean, there's
Why is that?
We'll probably go to that. Yeah, I think that's what we're talking about. That's your lunchtime. Are you able to put that
I'll make me share.
Oh, okay. You're in control.
Yes,
I'll trust your. I was just wondering whether you could make a screen so we don't have the audience. Or is
Been
that?
told to keep that in so for the recording. And this is the best way to make sure it doesn't obscure anything.
Okay.
But if there is too many songs,
Oh, yeah, so the other thing. The other thing is, this is like the virtual reality. So they have those, school kids coming in. So if you get too close. No one's ever been rejected.
But yeah.
Have our online numbers stabilized?
Oh, that's especially if you're in dark matter not tonight and had a very scathing first round report. So then it came back and it was quite interesting. It's like arguing that like basically you can get red noise from dark matter.
All right, hi everyone. We should get underway. So it is with great pleasure that we welcome to Swinburne Jayden Newstead. He's currently a postdoc at the University of Melbourne and works within the Dark Matter Center of Excellence under Nicole Bell in her group. Jayden did his PhD at Arizona State University and then went on to a postdoc there as well before taking up his current role at the University of Melbourne. He's from Melbourne originally, so he's from City, and I believe if anyone has a job in dark matter physics, he's currently on the job market as well. Anyone looking to employ someone, yes, please come to lunch afterwards and we will talk more. And so, as I said, Jayden works on dark matter physics, and so that's what we're going to hear about today, or the places you'll go. So I'll hand straight to you.
Right, thank you. So yeah, I wanted to give a fairly large introduction. So I'll try to put lots of introduction slides. But as we go through, then I'll move from reviewing the evidence. I think we're just going to have to not use this thing. We can take it out of slideshow. And then I'll look at. Okay, I'll just not use this. Not even the laser pointer. That doesn't keep happening. Move on to looking at why we're so interested in the particle nature of dark matter, and then more in line with what I do, I'll look at the direct detection of dark matter, what that is, and our current efforts in that. And what I was doing in writing this talk was thinking about how we synthesize all these different areas of physics into dark matter. As a student, that's sort of what drew me into dark matter. I was really interested in astrophysics, but then I really got drawn into particle physics. And dark matter was this big mystery that it brought together so many different things, like looking at cosmology, astrophysics. And then when you actually want to detect it, you got to look at the atomic physics and even the nuclear physics. So I really like how it brings together all these different parts of physics. Just a word on the title. The title is, I have a very young daughter now, which is just the you know, we're getting into Dr. Seuss. And there's this wonderful book, well, one that I remembered as a kid, Are the Places You Go. That's where I got the title from. So the grand view of the evidence, which is built up now over decades and decades, is that we have observations for dark matter, or just even more generally, this concept of missing mass across many orders of magnitude of scales and length scales in the universe. So starting at the largest scale, we've got observations of the cosmic microwave background, and that's like, it's the whole universe. You can sort of weigh the whole universe with that. And you find that there's about 15% of the matter is in normal baryons, and the rest has to be something else. When you look at galaxy clusters, which are obviously a lot smaller, you also find a similar amount, about 15% of the mass is normal baryons, or the stars, gas and dust. And then even on the smaller scales in galaxies, you find a similar thing, but actually galaxies tend to be more dominated by dark matter. And that's because of all the mess that baryonic physics tends to push baryons out of the centers of galaxies. And so they appear to have even more dark matter. And yeah, so this is like covering at least 6 orders of magnitude. And we do have some evidence for dark matter within the galaxy, but actually we'll get into like it becomes more and more difficult the smaller scales you look at to see dark matter locally. So I'm going to step through each of these, and that's not the whole introduction, one by one. So the cosmic microwave background. I'm sure you're all familiar with this. This has been observed in the sky in the microwave spectrum. It's very cold now. It's the leftover remnants of the very hot beginnings of the universe. And it is the surface of mass scattering. When the universe became transparent, it's very hot in the early universe. When hydrogen formed as an actual atom, the universe became electrically neutral, and you could have photons free streaming. And so this happened in about 300,000 years after the Big Bang. And it's actually, so I normally show a picture, you've probably seen this, where if you just show it at a normal level of contrast, it's extremely uniform. It's like it's a very, very, very uniform black body. And to get these pictures, you have to take very, very high resolution and careful measurements of the changes in temperature across the sky, and you find that there's actually these slightly cooler and warm spots, but it's at a level of like 10 to the -5 in temperature variations. It's actually extremely uniform, even though we like to show how it's not so uniform. But this is where all the interesting part is. Now, if you have a look at how these fluctuations change as a function of angular scale, so you can see there's some really large fluctuations, some big cold spots and some big hot spots. And I should say, I just did that backwards. Blue is hot, as in, and you're all astronomer and astrophysicists. Blue, like a star, is hot. It's proper coloring. And red are cool spots. Yeah, you find that there's typical scales. I'll use the shadow instead of pointing at the screen. There are typical scales where you get sizes of fluctuations. And one of the biggest peak you get in this power spectrum is at 1 degree. And that's sort of, it's twice the size of the full moon. That's sort of these size little dots. And that becomes a special scale. Now, why does this happen? Well, in the very, very early universe, when things are really hot, what this is little animation showing this wonderful set of animations by Wayne through on his website. If you haven't seen them, I recommend checking them out. What this is showing is, so we have a potential well, which is due to gravity. And just imagine that in the early universe, there's some density fluctuations. And that means that there's this extra matter in some places, and that creates gravitational wells. And those gravitational wells will pull baryons, these little balls, down into the centers of the wells. But when that happens, baryons interact with each other, they heat up when they go into overdensities, And photon pressure, which is represented by these springs, pushes back against it. And it actually sets up these oscillations. Now, if there's enough pressure built up, what happens is, it's not going to show us an animation, this one. Sorry, this one was meant to animate. What happens is it actually will spring back and push so far hard against the overdensity that it'll flatten out the potential. So in the very hot radiation-dominated part of the universe, so the earlier you go, the hotter it is, it was able to wipe out some of these fluctuations. And that happens on the smaller scales. And that is why down here you have a damping of this high tail. But at one scale, once the universe cooled enough, you had overdensities that formed due to dark matter, and they just grew and grew, and they produced these peaks that you see. So this is just another thing to show. It's to represent where these peaks are in terms of the angular scale. So this is basically like a Fourier transform. Don't know if that is okay. But just think about this as providing a filter on certain angular frequencies. And this is the plot of the picture you would see with just those frequencies filtered out. So on the far left, these frequencies are the very large fluctuations. And on the right, you've got the really high frequency fluctuations. Now, what does this got to do with dark matter, or like actually knowing how much dark matter there is? Well, you can actually predict based on an initial spectrum. You can evolve the universe forward, and you can work out based on how much dark matter and how much baryons you put into this universe and a few other parameters, what this power spectrum should look like. So what this is doing is just dialing up and down how much matter there is in your universe. And this is going up to be 50% of the critical energy density down to basically 0.05%. And that's showing, so as you have more matter, you have deeper potentials, and that suppresses more of the peaks. Now, what's happening here is that the amount of baryons and dark matter has been changed. And you see it seems to affect generally the entire scaling. But if you stop that at the amount of matter that we know exists, and then you just scale the amount of baryons, you can see how you start to change these odd peaks more pronounced. The baryons, due to the way that it affects these oscillations, affect the odd peaks in a greater way than the even peaks. And so if you stop this scaling at exactly the right amount to match the observations, you find that you've got about 0.02% of the universe in baryons, and there's about 12% of the universe in dark matter. So this is where you get the general thing. There's about 5 times as much dark matter as there is normal matter, and that's why. And the CMB requires this to reproduce this power spectrum. And cosmology's got this to incredible precision now. So this is the measurements from the Planck satellite, and yeah, it's at such precision now that this is like parts per thousand. It's very, very nice. And this is how we know, sort of weighing the entire universe, that there's a lot more dark matter than normal matter baryon. Okay, so stepping down onto a smaller scale, galaxy clusters, you can see in this image here, this is one of the first images where they showed a way to reconstruct the amount of dark matter due to gravitational lensing. So you can see this is a foreground galaxy cluster, and then here is a lens galaxy that's far behind. You can see there's nice big arcs. This is the same galaxy over here. And using some complex mathematics that I haven't really been able to understand fully, you can reconstruct the lensing potential. So this is sort of the schematic of what's going on. the light is bent by the gravity of the foreground galaxies. And you can work out how much matter is in this foreground lens just by looking at how the lens galaxy images have been distorted. And when you do that, you can reconstruct this image of the matter distribution. Now, the spikes there are the actual galaxies. But what you'll see is that there's a very smooth, large component which actually comprises most of the matter in this cluster. And that is dark matter, because in the image, it doesn't show up at all in light. Okay. Now, another interesting observation of dark matter in galaxy clusters comes from the Bullock cluster. So this is two galaxy clusters that have merged together. And if you haven't seen this before, just the actual image there is on the left. And what they've superimposed on the optical image is an image of the dark matter reconstructed for lensing in blue, and X-ray data, which shows the hot gas and baryons that were in the intergalactic medium. And this bow shot here, or this bow shot, is because the galaxies clusters actually pass through each other. So you're seeing this after a collision has taken place. So just to show you, this is not a simulation. This is just an artist's impression, but it does help to see what's actually going on. You have this smaller cluster come through a larger cluster, and you get this big bow shock form due to the drag of and the heat, and it gets heated up as all the baryons interact with each other. Whereas the dark matter, and actually the galaxies, pass through mostly unscathed. The galaxies are so small that they basically stack like little tracer particles, and they just come straight through. Now, this is an important observation, because you've got, at the same time as knowing that most of the matter is there in dark matter, you've also shown that it acts very differently from the baryons in this case. And it also shows that dark matter can't strongly self-interact with itself, because in this case, it's just passed straight through itself. Okay, so lastly, stepping down just to the size of galaxies. You may have seen this before, but this is the familiar picture. This is how dark matter was actually first well established as an observation, and by observing rotation curves of galaxies. So what is a rotation curve? So if you measure the velocity of stars as you step out from the center of a galaxy, and you make a plot of that, so this plot shows rotation velocity versus radius, then what you observe is that they're actually quite flat. It was very flat. The data lies in here, flat rotation curve, where the velocity seems pretty constant in the stars as you step out from the center. But as we know, just from very rudimentary analysis of orbits, like say in the solar system, if you have most of the mass concentrated in the center, then what you would expect is that the velocity as you step out in distance should go as 1 over the inverse square root. Now, in galaxies, most of the mass is in the center if you're looking at just the visible mass. But to be able to make this reproduce, this, so these components here, all these curves, are showing you different components as a mass model. So what they've got is the disk stars in dashed. We've got the bulge in dot dashed, which is peaked strongly in the middle. And then you have to add this component of dark matter here, which is steadily increasing, this halo piece. So at these lower radii, you don't find that there's that much dark matter. But actually, as you keep going in observations that measure further and further out, you can become more and more dark matter dominated as you go out in the galactic halo. And so, yeah, these observations show that you can't match these flat rotation curves without including some amount of dark matter into galaxies. Okay, so that sort of covers our 3 scales. There are 3 very different measurements, but one problem is that they are all gravitational. cosmology in the end is just using the Friedmann-Walker equations from GR. These using gravitational lensing and these using rotational velocities. They're all gravitational probes of dark matter. So yeah, it'd be nice to see it on the gravitational. But what we need to know in terms of doing experiments on Earth is what's the dark matter doing on smaller scales. And to that, we mostly turn to simulation. Of course, there are new observations of Gaia. I know Kieran maybe and I talked about that last year. I'm not going to talk about that, it's not my area. But one thing just to show you is that we do expect from simulations, and I know you guys do a lot of this stuff here, is we do expect a lot of these little micro halos of dark matter within the galactic halo. We do expect some substructure. I know this is ongoing debated topic, exactly what this distribution of the substructure is like, and it would be great to know for our experiments what that is. And then the other useful input is what's the velocity distribution of dark matter. Now we know it has to be something like this. This is the Via Lactea simulation, and it's in red. It's just showing the velocity of dark matter particles in a 1 kiloparsec shell, 8.5 kiloparsecs from the center of the galaxy that's meant to look like the nuclear galaxy. And the black dash there is the best fit Maxwell-Boltzmann distribution. So typically what we do as particle physicists, we just say, let's say it's Maxwell-Boltzmann distributed, and we use that as a first approximation. And simulations show that's not too far off. There'll be some higher order corrections that we will have to worry about, but for the moment, it's a decent assumption. And what you'll see is that also this thing cuts off at some point, and that's due to the fact that there's going to be some escape velocity, just the gravitational potential of the galaxy at the position of the Earth. So dark matter moving any faster than that would just leave the galaxy. And that number, based on observations, is around 550 kilometers per second for our position in the galaxy. So this simulation has it boosted into the rest frame, so you can add the Earth's circular velocity is a few hundred kilometers a second, so you can add a few hundred kilometers a second to that, and you get around the 750 mark, where you have a cutoff in the distribution. And these are all important inputs for later. What is the actual density of dark matter locally in the galaxy? So just to try and, this is a recent paper which tried to summarize a bunch of the measurements. And what you're looking at is, this is the density of dark matter for a whole bunch of different papers. And in the bottom, we've got particle physics units. This is, we say GeV per centimeter cubed. We put it in GeV because particles tend to be the masses of GeV-ish. And at the top, you've got the astrophysics units. You've got solar masses per parsec cubed, which I find harder to, it's funny how we just get used to how units to conceptualize. But the funny thing, they end up being these order, point something numbers. Yeah, so at the top here, going from top to bottom in this plot, we're basically going from observations which are very local to our solar neighborhood, down to sort of more global measurements of our whole halo. So you can see, obviously, the top ones, very top there, have very wide confidence intervals. And that's because as you're measuring closer and closer, you end up with fewer observations to really probe what the dark matter distribution is. And as you come down, you basically have to build models of the whole galaxy. And then you're just sort of probing what is the average dark matter density at our distance from the center of the galaxy in some model of the, yes?
Question.
Yeah.
That's the local density of the Earth. So how does that compare to the local baryon density?
It's a very good question. It's a very good question. I forget the exact thing, but it is entirely, at this point in the galaxy, are entirely dominated by baryons. It's like a factor of 10 or something more. Yeah. Yeah. Yeah, we're quite close to the center. In terms of the dark matter halo, we're quite, I should have shown on the previous slide. I did have a picture of this in another talk where you superimpose the actual Milky Way with stars, it's actually like here. It's just this little central bit. And this box is a very large box around the Milky Way. The galactic halo goes out to a couple of hundred, the dark matter halo goes out to a few hundred kiloparsecs. Yeah, so that is partly what makes this such a hard measurement. That you've got all these baryons, and you'd like to say they're traces of the dark matter distribution, but really they're dominating the potential in this part of the galaxy. And just to point out, at least we have some confidence that these are all probing something similar, and we're getting numbers that are somewhat consistent in the vicinity of 0.4 GeV per centimeter cubed. In particle physics, for a long time, we've just used this benchmark number of 0.3. That's starting to look conservative, which would be great, but we're not going to get our hopes up. We know there's a lot more work.
So 0.3 is the standard halo model.
Yeah, this is the standard halo model, which we'll follow. Every now and then you'll have someone point out that, oh look, one of these measurements with large confidence intervals, oh, it's consistent with 0 at 3 sigma. There could be no dark matter. I mean, that's strictly true, but we definitely don't know. We know there's dark matter in the galaxy. We don't know how lumpy it is. And if we end up with a void in our point, or in an overdensity. So this is very interesting work that's ongoing. So just to put that in context, so sort of to your question, but in a very local context, if you just look at the solar system, so the mass within Neptune's orbit. So Neptune is affected by all the matter inside its orbit. The sun makes up 10 to the 30 kilograms. So it's a large part of the potential. All the planets is 10 to the 27 kilograms. All the interplanetary gas, dust, bits of the asteroid belt only add up to 10 to the 26 kilograms. All the dark matter at that 0.3 GeV per centimeter cube density, you would only have 10 to the 17 kilograms inside Neptune's orbit. So if you call that the solar system, there's not that much. This is like the mass of a small asteroid or something, or a decent sized asteroid. Yeah, and then within the Earth, you've only got about a kilogram of any one point in time. There's like not much dark matter here locally compared to the barrier. Okay, so that's astrophysical evidence and context. So now I'm going to step into particle dark matter, which is more. Might have to speed up a little. I want to leave plenty of time for questions. So just to summarize what we know based on all those observations, because those really are all the observations of dark matter. We know it doesn't interact with light, which is pretty obvious, but it just doesn't appear in the pictures. So it must be electrically neutral. It must be stable on cosmic timescales because we know it was there during seeding structure in the early universe. So it must have a lifetime of greater than, I don't know, 10 to 10 years. Maybe there is some wiggle room there if it's decaying slowly. It can pass through matter and itself. It seems to just go through the Earth or whatever else, and even itself in the Bullet cluster. So it has to be very weakly interacting. It can be decoupled from matter, as in like in the Bullet cluster, it showed that you can sort of pull it away from the matter. So that's sort of a big thing in saying that it's hard to modify gravity and also come up with the same answers. So a lot of people there's always a few people who say, why can't we just change gravity if we understand gravitation? Well, there's a lot more that goes into this, but one of the reasons is that you can see that dark matter can be decoupled from matter. And lastly, we know that it clumps up nicely and can be bound to gravitation. So that means it's cold. It's become non-relativistic. So it doesn't just fly away. We know, like in this galaxy, velocity distribution is like, has it moving at hundreds of kilometers per second, which is going to be non-relativistic. So that's why we call it cold dark. So the standard particle dark matter paradigm is that you have some relic in the very early universe, which could have been thermally produced or otherwise. To say it's thermally produced, I'll go through an example in a minute. Just means that it was in equilibrium with all the other particles, the baryons and the photons. And at some point it decoupled from them. But there are other ways to produce it that are non-thermal. But we know that it must have decoupled basically before or around the time of Big Bang nucleosynthesis, because we have very good predictions for that. And basically, you can't add more baryons to that. You can't add much else that's in contact with the baryons thermally at that time. And that happened like 10 seconds to a few minutes after the start of the universe. So dark matter is already decoupled and just acting as a background potential at that point. Yes?
You just said this, but I was wondering what does actually mean by decoupled? Because assumption is that dark matter does not interact with gravity anyway, right?
Yeah, so decouple in this sense just means if it ever did interact with particles.
Right.
So at high temperatures in the very early universe, so interaction strengths can change. In particle physics, if you have very high energies, you can actually increase cross sections, or you can have phase transitions that happen and change things. So it's possible that in the extremely early moments of the universe, dark matter was in contact, like it was actually bumping around, hitting particles. But then at around 10 seconds or so, some sort of transition happened and we say decoupled, meaning after that point, it only interacts with gravitation with everything else. And it's no longer in thermal equilibrium with the standard model particles. So it's not colliding with it. And all it does is provide this background thing to seed structure formation. And what we know based on, on the right is every particle in the standard model of particle physics. What we know based on this is that all the quarks at the top here, all of the charged leptons all have electric charge. And basically you're only left with the neutrinos that are neutral. And to be able to say that it is cold and it will help seed these density fluctuations, we needed to have some amount of mass, which will let it do that in these early times. And neutrinos just can't do that. They're so light, they're always relativistic. Even if they've only got very cold temperature, they'll still be relativistic. So we know that it's not neutrinos. And so the standard paradigm of particle dark matter is that we need some new particle. The standard model is incomplete. We need to add some new particle which will do the job of dark matter. And this is just, I just took this from a community sort of white paper review article, which just summarized a bunch of the different candidates for dark matter. So we have a whole lot of different candidates. And what this picture is showing a scale of is the mass of the dark matter particle. It's the same scale above it. So on the far right, we've got things which have solar mass size. I mean, that is just black holes in that category, primordial black holes. And then as we move down, we've got like the familiar sort of GeV scale particles, KeVs, like electron mass, and then neutrinos are EV mass, and then we go all the way down to very, very light particles. Now we know in general in particle physics, you can't have a thermal dark matter particle, which is more than a few TeV in mass. That's due to a theoretical issue. That's why things tend to hang there. And then at the very, very low end, you've got these types of dark matter people called ultralight dark matter. Now you can ask them like, oh, didn't you just say you can't have very light dark matter? So these types of dark matter are a bit different. They're produced differently. They're produced cold. They're cold relics, and they set up what's called wave-like dark matter. It's a very different type of dark matter. They may not fully reproduce the observations. So they are of interest, but they're probably less studied. QCD axion is very, very hot topic because it's a nice theoretical thing. So I'm going to mainly talk about dark matter in this region here. And there's a whole bunch of different theoretical models you can write down to do that. The classic is WINT, which stands for Weakly Interacting Massive Particle. And so I'll talk about that now. Okay. So yes.
Just really, I've never heard of that.
Oh no, sorry. Yeah. The other thing that was overlaid, and I was almost going to cut this out because I didn't have to explain it. In red, they're showing anomalies. So there's an anomaly in decays in beryllium-8, which points to there being some new particle that's about 10 MeV or something. Yeah, so you could explain this anomalous decay if you have some extra particles. Muon G-2 is it's the magnetic measuring the magnetic moment of the muon, which at the moment is very different from the prediction. The measurement is very different from the prediction in the standard models, so there could be some new physics there. And the small scale structure, I'm not really sure what they're doing about. Yeah. These are just anomalous things that people have tried to explain with dark matter that provided a benchmark. Yeah, and so green at the bottom is the type of experiments that probe. So it moves from the very cold experiments to standard direct detection, nuclear atomics, and then accelerators for the higher energy part. And then to probe the black holes, you've only really got microlens. And just to put just one word on this, people have searched for primordial black holes for a long time, and it looks like they're pretty well constrained over a very wide mass region. There's a little small mass region around this area, 30 solar masses where you can maybe have some of the dark matter there, but it's hard to accommodate all the dark matter as primordial black holes these days. Okay, so producing dark matter in the early universe. So I'm just going to go over two production mechanisms. So just focus on the solid lines right now. Along this axis, we've got this parameter, which is the mass of dark matter divided by the temperature. Forget what that is as a scale. Just know that as you move to the right, you're moving up in time. So the universe cools, this number goes up, and time goes forward to the right. And the vertical is the density of dark matter in the universe, and this black line with Planck written on it is the measured amount of dark matter in the universe. So whatever you do, when you're done with whatever's happening in the early universe, over here, you need to end up on that line. Okay, so what we call standard, we're doing freezing first, and we'll come back to freeze out. So to freeze in dark matter, you start with no dark matter, all the abundances are 0, and you slowly produce dark matter in the early universe, and then you have to have a mechanism which turns it off at some point. And you can do that. Actually, you don't even really need to fully turn it off. But basically, when the universe cools to a low enough temperature that it's below the mass of that particle, then you no longer have the energy to make it just by bashing particles together. So then really, you basically have one parameter you need other than the mass, and that is what's the interaction strength. So you need to tune the interaction strength to be just high enough that you produce enough dark matter as you go forward in time. If you have a number that's too high, so this is, don't worry too much about the scale of the units, but this is a cross section. If your cross section is too high for producing it, then you'll make too much dark matter and you would overclose the universe. If the cross section is too small, then you don't produce enough dark matter, you won't get structure formation, and you can't explain everything. So on the left side, freeze in, you need to tune the cross section to sort of be directly proportional to your abundance. Freeze out does the opposite thing. Freeze out, you start with lots of dark matter on the left. And that's the situation I was saying before. It's sort of the dominant picture that it's in thermal contact with the standard model in the very early universe. You've got a big bath, particles, dark matter is in that bath, buzzing around. And then as time marches forward, the universe is expanding, it's cooling. Dark matter starts to, what we say, freeze out. So at some point, the bath becomes too cold to produce dark matter particles. But dark matter keeps annihilating with itself because you produce dark matter and anti-dark matter. And so this is the annihilation cross-section that's given to us. And if your annihilation cross-section is too low, then you're left over with too much dark matter and you'll overclose the universe. The annihilation cross-section is just right, you get this green line. And if the annihilation cross-section is too large, you'll over-annihilate dark matter. You'll have not much left over, and you can't do structure formation. So both of these scenarios are just two pictures of how you could end up with the right amount of dark matter, and you have to fit to some cross-section then in your particle physics model to reproduce the observation. Now, if you've heard of what's called the WIMP miracle, it is the fact that this number here you can get as a cross-section, you calculate it by just putting in weak scale physics. And by that I mean particles like the Z boson stuff you're probing at the LHC, at those sort of energies, if you put in those interaction strengths, then you can get that number very easily. So in a way, it was considered a miracle, or sort of a natural answer, because when it was supposed, we didn't know what weak scale physics fully was. We hadn't discovered the Higgs yet, and people sort of expected that maybe there'll be supersymmetry, maybe there'll be something else there that'll complete the picture of the particle physics model, and that could also easily give us dark matter if you have some new particle at that scale. Now, so far at the LHC, dark matter hasn't shown up. We'll talk about that more now. So we want to detect dark matter. I don't know why I cut off some of my my pictures. What this is meant to show on the left is two fermions being smashed together, and you can produce dark matter at something like the LHC. So these are colloquially known as make, break, and shake ways of detecting dark matter. So you can make it at a collider by colliding two fermions. That's meant to be an F at the top, and you get two dark matter particles out. In indirect detections, this is something like the alpha magnetic spectrometer, which is there on the it's over here on the International Space Station. And so that is, you're looking for dark matter breaking, as in, so you have two dark matter particles come in and annihilate, produce some particles you can observe. Or last of all, shake means you have some dark matter come in and hit a fermion in a detector. So we have these big underground detectors, I'll talk about that in a minute. And it'll produce some detectable signal when dark matter bumps into something in the detector. Okay. So how do you do this in a collider? Well, so we have these beautiful large detectors. This is a CMS detector at the LHC, and they're colliding protons, and they get these lovely images of where all the particles that splash out of these high energy proton collisions. Well, dark matter, we already said, is extremely weak in vacuum, so you would expect that it's just going to leave the detector. But actually, that is detectable because it comes up as missing momentum. So your initial two particles coming in basically have zero net momentum. So if you if you add up all the bits and pieces coming out of your collision and you look for some, non-conservation momentum, you could discover a particle that way. And this is analogous to how neutrinos were first observed when they noticed that there wasn't enough momentum to explain beta decay. So it's hard to truly discover dark matter because all you know is that there's missing momentum. You don't know that that particle coming out of the collision is the dark matter that's in the galaxy. So in that sense, it's not very useful in actually discovering dark matter, but it's extremely good at excluding dark matter. Because if dark matter exists in that mass range and it's coupled with the same model, it will get produced in the collider. So it's good at excluding possibilities of dark matter, maybe not so good at actually discovering what is the dark matter in galaxies. So this by break, I mean, so you're looking for annihilation of dark matter. So this is just two little cartoons. You could annihilate, and you could produce fermions through some higher order loop process, produce photons, and that could be observed by something like the Fermi telescope in orbit, or you could annihilate and produce some charged particles like electrons or protons, positrons, which instead of just nicely propagating to your detector, they get really messed up in the galactic magnetic field, take a long circuitous route, and end up at a detector like the AMS, alpha magnetic spectrometer, on the International Space Station. The difficulty with this is, so this is the 2-year map, all-star map of Fermi. So there's a whole bunch of astrophysics going on in the disk, and you've got a whole bunch of sources, some of which have been identified, point sources. And here on the right is someone's taken, this paper here, one of these simulations of dark matter, which showed all those little microhalos. And basically, if you calculate then what should be the flux of photons coming from those if they're annihilated, this is what a map of dark matter annihilation should look like. So you'll have lots in the center of the galaxy, but you'll also have a bunch of these little microhalos. So being able to pick this out of this is extremely difficult. People have tried, but basically you run into a whole bunch of problems. And there are some anomalies, interesting anomalies in the data, but as yet nothing is very convincing. We don't know what the distribution of pulsars is through the galaxy, which also produce a lot of gamma rays. So while there's a potential for like a smoking gun, if you had have seen like, something that you just couldn't explain astrophysically, some gamma ray line at some energy where dark matter is annihilated and produced a line in your gamma ray spectrum. There was a potential for that, but now it's getting harder to imagine that we'll just suddenly find this smoking gun. So astrophysical backgrounds have made this problematic search for dark matter. That brings me lastly to shape. So what we're looking for here, dark matter, which doesn't interact very strongly, could just come straight through the Earth and bump into a nucleus or an electron in your detector and leave a little deposit of energy which you observe. So in this, you can have an extremely controlled, this is your own lab, so you can make it as controlled as you possibly can, have very low backgrounds. And so you can, in this case, look for a smoking gun in that there's a few things we expect from a dark matter signal. And that is, we expect an annual modulation as we go around the sun, the flux of dark matter increases and decreases as you go into and out of the dark matter so-called wind. And there would also be a direction signal. There is an asymmetry in the direction of the dark matter particles, which you could also look for. So I think this has the greatest potential actually discovering the dark matter in the galaxy. So that's what I've chosen to work on. And these sort of experiments actually get called the quietest places in the universe, just because so much effort has gone into shielding these things, putting them deep underground, using radio pure materials so that there's just like basically no backgrounds. And they got it down to the point where in the detectors, there's something like only a handful of events in a ton of detector material throughout an entire year in terms of nuclear recoils. So this is just a stunning achievement in terms of reducing the number of background events that happen inside this detector. Okay, so how long have I got left? We're really running out of time. Time for questions. But I'll just do a little bit on my work and what these detectors do. So one type of detector, which we've joined a future collaboration, the Darwin collaboration, to build a large-scale version of these detectors. What it does is when a dark matter particle, or actually any particle for that matter, collides with an electron or a nucleus in the detector, you produce some electrons, and you also produce some scintillation photons. So what you get is you actually get two signals. One you call S1 is prompt light that comes out, and then the electrons you drift out with a drift field. So you pull the electrons out, and then you get a second flash of light when the electrons reach the surface and you extract them from the liquid. And you get two little pulses of light that are separated in time. And the separation in time lets you work out how deep in the detector it happens. And then the pattern here on the detectors, so they have PMTs on the top and the bottom of the detectors. The pattern lets you get the X and the Y component. So you get full X, Y, Z information on each event. And so they're called time projection chambers, these type of detectors. And then another important part is that the relative size of the S1 and the S2 signal, the amount of electrons you produce versus photons, if you put them onto a plot where this is the number of photons produced, this is the amount of charge, nuclear recoils sit down here on this red curve, and electron recoils sit up on the blue curve. So that's just two separate calibrations, one of electron recoils and the bottom of nuclear recoils. So this helps you eliminate electron recoils, which are a harder background to get rid of, turns out, than nuclear recoils. We generally expect dark matter to interact more strongly with the nucleus. So it's good that we can make the nuclear backgrounds, recoil background very clean. Okay, so what goes into, I'll just very quickly go through how we calculate how dark matter interacts in the detector. So this is a differential rate. So it's the number of events we get per kilogram detector per day per keV. So we're talking about spectrum here with respect to the recoil energy, the amount of energy it deposits in the detector. So the first component here is coming from particle physics. It's a cross-section in the masses. The second component here comes from the nuclear physics. It's to do with the target, and there's a thing called the nuclear form factor in there. And then this last bit is the astrophysics, which I talked about earlier. You've got the density of dark matter and then the velocity distribution, which affects how, the incoming energy of the dark matter affects how much energy it can leave in the detector. So just stepping through this, when you calculate the form factor, you can do this by the first order approximation. It's the Fourier transform of the charge distribution. If you expect that the charge distribution models where there's mass in the nucleus. And so if you have a model for the mass in the nucleus, so I've just given 2 examples. This is just a mass distribution as a function of the radius of femtometers inside a xenon nucleus. So you can have a few models of that. You take the Fourier transform and you get this thing called the form factor, which shows up in scattering theory. That's unfamiliar to you. Don't worry, I just wanted to give you a peek at how nuclear physics enters the calculation. So now what does the actual rate look like? So if we plot, this is the rate as a function of recoil energy. So it peaks at very low energies. This because it's elastic scattering, and we have a general fall off in energy as there's fewer particles that can impart larger recoils. And this is just 2 examples, 2 masses of dark matter, for example. All you'll notice here, KeV, this amount of energy is very small when it's in terms of a nuclear recoil. A KeV photon is pretty easy to see. The KeV of a nuclear recoil is just like, it's a nucleus just moving a bit faster through the liquid, say, of your xenon detector. So it produces a few electrons, a few photons that you have to try and detect. Now, just to introduce to you what the parameter space that we look at when we're trying to understand if we're constraining or ruling out dark matter, is we plot this cross-section here. This is that cross-section that shows up there. It's an overall scaling of the strength of dark matter interacting with protons and neutrons. And then this is as a function of the mass of dark matter. So we don't know what the mass is, so we plot this as a function of the mass of dark matter. And then this is the constraint. So everything above this line would be excluded when you do an experiment, which say, so this is just for an example, when you have one event, if you have dark matter with this cross-section at this mass, it's like 50 GeV, a few by 10 to the minus 45 centimeters squared, then you have like 1 event per day per ton of detected material. And that's about where the current sensitivity is down here somewhere. Because they've ran these experiments for about ton scale experiments for about a year, and basically they haven't seen any. So the current constraints are now pushing down to this blue curve. And so basically the challenge of these experiments is build them larger, make the backgrounds lower, and we can start to push down and exclude weaker and weaker interacting dark matter. And I should just say that there are models of dark matter that are way down here, and so that's why there's this ever increasing effort to just try and see more and more sensitive, make more and more sensitive detectors. Really, now the last few slides. There is a problem with very light dark matter, and that is that as a mass, it doesn't have much mass, it doesn't have much kinetic energy. And so it's not able to impart much of a recoil in detectors. And that's led to some recent work where we try and look for what's called the Migdal effect. So where dark matter interacts with the nucleus, and that causes an electron to be ejected from the outside atom. This is distinct from the electrons I was talking about before. It turns out that these type of electrons are easier to observe. So I'm going to skip over the history of that. And basically, what it allows you to do is you get these higher energy electrons getting spat out of nuclear collisions, and these might be easier to observe. Okay, so I'm really just going to skip to the end. This is something we just published very recently, where the idea was that if you put hydrogen inside your xenon detector, hydrogen is a very light atom that's easier to bump around. And if you make use of this thing called the Migdal effect, you're able to, this is a projection, the red curve is ours, to say you're able to exclude very light dark matter with these big xenon detectors. And if you build them larger, which they're planning to do, you can really cut down into this space, this big white space here where nobody has excluded. All the gray curves at the top there previously excluded regions by other experiments. Okay, so just to summarize, we have evidence for dark matter that covers, many scales in the universe, but it's only gravitation. So particle solution is favored for this problem. We have 3 ways to probe it that I covered. Direct detection, I believe, gives us the best chance of actually discovering what the dark matter is. And there's a rich amount of phenomenology to do to discover, to find out what these dark matter particles are and improve the sensitivity of these detectors. So thank you. Yep.
Okay, questions from students?
Thanks for the talk. By the way, I want to ask about the scattering event rate equation. If we ignore about the astrophysics, what will be the equation?
We can't really ignore the astrophysics. So you mean?
Yeah, I want to ignore the astrophysics event. So what looks like the equation after that?
Well, so you need a density, that row, you need some density. At the moment, that we're saying that comes from, it's produced by just the dark matter that's in the galaxy. So you need that. If you had some other density that you could put in, say like if you produce dark matter, then yeah, you get a slightly different equation where, so actually there's a cross section times B, which is like a flux, times rho, which is the density. So you get like a flux of dark matter. You can change this calculation, remove the astrophysical part, and put in your own flux of dark matter, which you would have to create at something like the LHC or some other collider where it's potentially making dark matter. So you can replace that term with a flux coming from an artificial source. But the problem is you don't actually know if you're making dark matter. So you gotta have a theory, predict how much dark matter you're making, and then go and try and make it, and then try and detect it. So there's extra unknowns there. People actually do those calculations. I've done some of them. People don't tend to build experiments just to do that, but if you can use other experiments that are already running, then you can actually constrain dark matter that way too. Yeah.
Thanks.
Robert?
Yeah.
Same question, but for the event rate. So in your experience, what's the biggest source of uncertainties? Because I do simulations and we can try to improve the standard halo model and you find that, oh, actually these new observations found that there's obstruction in the local universe and that can affect the amount of density maybe by increasing a little bit.
Yeah.
But I had to do calculations in quantum field theory, and that's, I feel like that's a bigger source of of uncertainty. So where should we push to bring it to more accurate?
I'm interested in pushing on both fronts. In terms of strictly just like the uncertainty, like if I have a dark matter model, depending on the model, you can actually do a pretty good job at calculating what the cross section is. You can add loop effects, which people don't bother to do generally because your first tree level calculation tends to be a few percent accurate anyway, except in certain circumstances, but generally it's a few percent accurate. The nuclear physics, if you're doing what I didn't really explain, this is called spin independent scattering. It's just very standard. It scales with the number of nucleons in your nucleus squared because you have coherent scattering from the nucleus. For that type of scattering, we do expect that the nuclear uncertainties are pretty low. But if there's a different type of scattering that's spin dependent, and it couples to the spin of the nucleus, then the uncertainties go up a lot. And there's a lot of work ongoing to improve nuclear models. It's very difficult for things like xenon, which are huge nuclei. But that is ongoing work. Now, on the flip side, the astrophysical context is sort of I'd say it's a bigger unknown, but we know that the dark matter distribution must be lumpy on some scale. We just don't know what the size of that is. And as you saw by those different measurements, that many of them will give you these big error bars, but then the error bars don't even overlap in a lot of measurements. So you don't even know, should I just average all of them together and put a big error bar? Or we're not really sure what to do there. The good thing is that at least in terms of the density, most of those are within a factor of a few of each other. So yeah, if your uncertainty, if you're wrong by a factor of 2 in the density, it just means that this curve, which is on a log scale, moves up by a factor of 2, which isn't like a huge deal. It's a fairly tame uncertainty, and it just scales everything. The velocity distribution comes in as a large uncertainty in the low mass dark matter, because there you're really sensitive to the tails of the distribution of the Maxwell-Boltzmann, whatever velocity distribution you have. And so that is something that would be very interesting to learn more about. Because yeah, the uncertainties blow up and you get orders of magnitude uncertainties on the low end.
Astronomers love log scales.
Yeah, it hides a lot of things.
Yeah, we don't say that. Let's go online quickly. Mark? We can't hear you, Mark.
Sorry now. How's that?
Yep.
Yes.
Good. Yes. I've always been a bit puzzled about these direct detections where you expect a seasonal effect. The idea being you move up into the wind and away from the wind as you go around the sun. Is there anything to say that the dark matter on average is stationary or pressure supported rather than rotational? It's just that everything else in the universe rotates and our galaxies do. So you expect when the halos are forming, they would spin, just like gas when it settles into a disk of a galaxy. So is there anything to say that the dark matter is not just ambling along with the stars, or they're all dragging each other together if it was only just a gravitational effect? I know that the baryon quantity is, a fair bit less. Well, actually, it's not, is it? It's dominant. So wouldn't that tend to drag the dark matter around with it, and therefore you'd get no wind?
Yeah, no, that is totally an open question in terms of what's the baryon feedback on dark matter halos. So those simulations are very, let's say, primitive, they're very early. In general, when the halos form, they tend to have very small rotations. And this is because the dark matter doesn't have a way of dissipating energy. So when they form, the halos sort of naturally form into these like pressure supported, or not pressure supported, just these virial velocity supported structures where there's not a lot of rotation. Since there's no way to dissipate energy, the dark matter doesn't collapse down. And when you collapse down is when you typically get things spinning up through conservation angular momentum. So they tend to be only rotating, say, like 10 to 20 kilometers per second. And then otherwise the velocities are random. And then, yeah, it's the baryons moving through it at quite a large velocity gives you this annular seasonal effect. Now, you're right. It would be interesting to know if when the simulations get better, whether there's some feedback that stirs up the dark matter from baryon effects. But from what I've seen now, the simulations don't tend to show there's a big difference.
There are like adiabatic contraction and so on, where you can get these sorts of interactions happening where the dark matter can be distorted from its sort of natural what it would otherwise be doing. But this is
you definitely get, so in some of the simulations you get these large streams, and there's even some evidence in Gaia data that we have some streams, at least streams of dark matter from time instruction.
Yeah, but not on a sort of total galactic scale.
Right. Yeah.
No.
Sorry, last question.
Okay.
Yeah, so I was wondering about this plot you have here with the detection sensitivities. So in astrophysics, we normally assume cold dark matter. And so like these experiments are presumably ruling out like more massive forms of dark matter. So where would like cold dark matter sort of fall on this, assuming that we have, the correct dark matter density and we haven't just landed in a local region where there's not much dark matter?
All of these masses here, dark matter will be cold. So I'm not even in the range. If you get down below, I think it's about 150-ish MeV dark matter. So it's down here somewhere. You start to get what people call warm dark matter. And then as you go down to KeV is where you get things like hot dark matter. So this is all cold dark matter, this region.
But in terms of like the interaction strengths, what would be?
Oh, so what would we expect?
Yeah.
Yeah, so if you have I should have shown a plot of this. you can make some particular models which will give you like individual curves that go through this. And if I try and like just wave my hand, it'll go something like this. It'll come up here, it'll get stronger, and you'll have some dips here if there's some resonance effects, and then it goes up here. So we're definitely, so the current experiments, which I'll show you another plot, is cut in mass, but this has actually got some current experiments on it. These are actually cutting through space where you would expect there to be some dark matter. But there's also models where it's well below that curve as well. So I'd say we're in a good region where if dark matter showed up in this experiment, we wouldn't be like, wow, how do you do this? Like there are theoretical possibilities to do it. But we've also got some benchmarks that are just ahead in the sensitivity that entice us to keep going. So we're not giving up yet.
We do need to finish there. We will be going out to lunch at 12:30. So please, if you're interested, quickly send me an email just so I can make sure that we can book a table depending on the numbers. But we'll meet out front here of the AR building. But with that, let's thank Jay again. As well, so if you wanted to continue conversation.